பரவாயில்ல, அது உங்கள் இஷ்டம். Hello students, welcome to IMS Academy. But in the foundation course I started electronic devices and circuits. This is the part 4. But I started semiconductors in EDC. So far completed 3 sessions, this is the 4th session. But I completed before what is an insulator, energy band diagram of insulator, and also I did the conductor, what are the parameters in the conductor, energy band diagram of the conductor also explained. In the last class in the last session I started semiconductors. There I explained about what is semiconductor, how the energy band diagram, how the energy band gap will be changing based upon the temperature, that also I explained. And also I explained atomic concentration and also how to find out the concentration of electrons. Up to that extent I have done the work. Good evening Madan. But the work I have done already. But in today's session, how to tackle the problems based upon the atomic concentration and also concentration of electrons, you will see then. And also I am going to explain mass action law also today, and certain derivation based upon the intrinsic semiconductor, I will do it, understand now. Before going to this subject, just I want to give some information regarding the IMS Academy. The students who are willing to take admission in IMS Academy can make a call to this number. Every information you are going to get. But if the students takes admissions in the IMS Academy, what those benefits they are going to get that I want to give. Program futures I am going to give here now. More than 800 hours of the live classes with live interaction possible. The IMS Academy provides theory book, exercise books to the students. The exercise book contains more than 4,000 questions. I hope these are the questions are just enough to crack the gate. It is not required any other textbooks. If you are practicing the questions of this 4,000, it's quite okay. Understand my point now. And also the point what I wish to say, in this exercise book it is given 3 level questions. Level 1, level 2, level 3. Level 1 is a basic level. Level 2 is nothing but the somewhat good level questions you can find. Level 3 is a very complicated question. The students, those who are willing to get a good command on the subjects, they need to do the level 3 also, understand now. Up to level 2, if you did it is quite okay to crack the gate. Level 3 is more than the, but now gate level it is given, understand now. Very good questions I said now. and also more than 34 years gate question banks with video solutions. Every gate question, but GQB book will be given to the students. The Miss IMS Gate Academy provides gate questions bank. But in that book, all the gate questions were solved. And also alternative solutions are given, and also video solutions also given for certain questions here now. 12 personalized one-to-one mentorship session possible now. That means each student can get a chance to discuss with the faculty here now. And in the mentorship session, the students can get the information regarding the how the preparation to be made, and initially what those subjects are to be started, and what period of the time it is to be taken to complete each and every one of the subjects. Those suggestions will be given by the mentor. So around 12 personalized one-to-one mentorship sessions possible. More than 130 online tests with video solutions of the mock test and many more. So what I wish to say, if the students wants to get admission in IMS Gate Academy, you call to this number. Understand? You will get the every information from there. Understand? Okay then. Now we can start the subject. But in the last class I explained atomic concentration. But based upon the atomic concentration, I would like to do the question. What I gave it, just I want to explain once again that atomic concentration to tackle the question here now. Atomic concentration I'll give atomic concentration. Atomic concentration means I said number of atoms per cm cube. To determine this formula will be useful. Atomic concentration equal to, I gave it already, A naught into D divided by A. I gave you a formula already. This is atoms per cm cube it comes, units. Atoms per cm cube is possible. But A naught equal to, I said, its value is fixed value, 6.023 into 10 power 23 Avogadro number. D is the density, I said already, density I gave already, and A is nothing but, I gave it as a atomic weight. Atomic weight. The information already given to you. Now based upon this formula, we need to do one problem, one or two, three problems I will do now. For the germanium and silicon, I would like to find the atomic concentration. I'll give the problem now. A problem is given here now. Find atomic concentration of, find atomic concentration. Atomic concentration of germanium. I am asking for germanium. For germanium. For germanium I want given atomic weight equal to atomic weight is given here 72.6 is given, atomic weight, and density of this material is given. Density is given here now. This is 5.32 grams per cm cube is given, grams per cm cube, and the information is given here now. We need to find out the atomic concentration of germanium. Just now I gave you formula. Atomic concentration is denoted by AC. Atomic concentration is nothing but AC, I said. I would like to take it as AC, atomic concentration. Atomic concentration equal to what I gave it, A naught into D divided by A. This formula is given before. So we can substitute all the values here given. But A naught is nothing but, you know very well, 6.023 into 10 power 23 is given. And atomic and density is nothing but the 5.32 is given here. 5.32 divide by atomic weight. Atomic weight is given 72.6. 72.6. Use calculator, you will get atomic concentration of germanium. I will put germanium atomic concentration. Atomic concentration of germanium. I am putting now. For germanium, I am finding the atomic concentration. How much value? Use calculator and please tell me. For germanium, its value is 4.4 into 10 power 22 atoms per cm cube possible. Atoms per cm cube. This is the solution for this question. I hope you followed. This is the solution for germanium I gave it. And I would like to give one more question. You please try to complete. Next question. Find atomic concentration. Atomic concentration. Find atomic concentration of silicon. Of silicon I am asking. Of silicon here given. Of silicon. But for this silicon it is given, for silicon it is given atomic weight. Given atomic weight. Atomic weight. Atomic weight is given 28.1. 28.1 it is given. That is the atomic weight of silicon it is given. And density is given here. Density of the material. Density is given as a 2.33 grams. 2.33 grams per cm cube is given. Grams per cm cube is given. Grams per cm cubes. That is the density. But it is asking to find the atomic concentration of silicon. How we can find? The same formula is applicable here. By applying the same formula, we can get answer. Anybody can tackle this question without my help? Any student can do. But I gave you formula. I gave you formula. For silicon, I want atomic concentration. Atomic concentration of silicon. Formula is given A naught into D by A. This formula is given already. By using this formula, you can determine directly. Then I can use silicon atomic concentration I want. A naught is nothing but 6.023 into 10 power 23, you know, A naught value. It is a fixed value. 6.023 into 10 power 3 into density is nothing but 2.33 is given in the problem. Divide by A. A is nothing but atomic weight 28.1. Use calculator. If you are using the calculator, you will get 5 into 10 power 22. 5 into 10 power 22 atoms per cm cube. Atoms per cm cube is possible. Like that, you can determine atomic concentration of silicon. I said already, but atomic concentration will be useful to find out the concentration. That concentration, how to get, I will give with one problem. Yes, next question. The specific gravity of tungsten. The specific gravity of tungsten is tungsten is nothing but the conductor only. Conductor is 18.8 grams per cm cube. Specific gravity can also be said as a density only now. Understand now. If each atom is having, and its atomic weight, it is given, and its atomic weight, is 184 given. If each atom is having two free electrons, calculate electrons concentration. Electron concentration I want. This is the given question. Any student can get answer for this question. Anybody can try what way to get answer for this question. It is a very simple question. What's given in the problem you watch and what he is asking to find. First I will note down the data. The specific gravity of tungsten is given. The specific gravity can also be called as a density. The density is given as a 18.8. 18.8 grams per cm cube. Is given. And also its atomic weight is given. Atomic weight, density means I can put a D. Atomic weight means A. There is a 184. 184 is given. But each atom having two free electrons. Free electrons are two here. How many free electrons in an atom? Free electrons per atom only here now. For each atom per atom equal to 2. But is asking calculate the electrons concentration. Electron concentration means N equal to how much? Electrons concentration, how much is asking to find. But I gave already one formula in the last class. The atomic concentration into number of free electrons, but the free electrons per atom can give concentration here now. Concentration you can get now. That's why here initially what you need to find atomic concentration is required. We can find atomic concentration at first. Atomic concentration I want to find. You know the formula for the atomic concentration, A naught into D by A. But A naught is nothing but 6.023 into 10 power 23 into density is nothing but 18.8 divided by A. Atomic weight is nothing but 184. Use calculator. Use calculator and tell me its value. Its value comes as 6.15. 6.15 into 10 power 22 is possible. 10 power 22 atoms per cm cube possible. Atoms per cm cube is possible. Atoms per cm cube is possible. By using this you can measure, by using this we can measure electrons concentration. I want electron concentration. Electrons concentration. That is nothing but N. That is nothing but N. I gave it atomic constant. This is atomic concentration AC. AC into what I gave it? AC into free electrons per atom. Free electrons per atom. Atomic concentration I got as a 6.15 into 10 power 22. Free electrons are 2. Multiply that. And finally you are going to get 12.3 into 10 power 22 per cm cube is possible. Per cm cube is possible. This is the solution for this question. Like that we can calculate only now. Next one. That way we need to calculate this value. Next one. But the two types of the semiconductors we are using. But two fundamental semiconductors I gave it. Germanium and silicon. But which one we are using mostly means anybody can say silicon we are using mostly. But you should understand the comparison of silicon and germanium. From that you can understand why so used silicon in practical application as compared to germanium. Each and every point I will give. Comparison of silicon. Comparison of silicon and germanium. These two I wish to compare. How I will compare this, you watch it. I will not take any table. Directly points wise I will give now. But which is stable at high temperature? High temperature, at high temperature which material is stable? So silicon is highly stable as compared to germanium. Up to what temperature silicon can withstand? Up to what range of temperature is maintained by up to what temperature, what range of temperature it can accept this germanium I will give you now. You can understand clearly. First point, silicon is highly stable. Silicon is highly stable. Highly stable. Highly stable at high temperature only. At high temperature. At high temperature. Highly stable at temperature means what range of temperature it can maintain. It can withstand up to what temperature we can see for silicon and germanium also. In silicon, temperature range is the same point. In silicon, temperature range, that means within this range of temperature it can withstand. In silicon, temperature range is minus 60 to 175. 175 degrees centigrade. Within this temperature, it will be stable only now. That means up to 175 degrees centigrade, it can withstand only now. Understand now. But while for germanium, we can see, while for germanium, while for germanium minus 60 to minus 60 to minus 75 minus 60 to 75 degree 75 degrees centigrade only possible. But it can withstand up to the temperature of 75 degrees centigrade. The stability of germanium is possible up to 75 degrees centigrade. The stability of silicon is possible up to 175 only now. So the range of the silicon is more only now. That is one of the point to use silicon in designing the electronic devices as compared to the germanium. I can say that now. That's the first point. Second point, you must understand, power handling capacity of silicon is higher than the germanium only. Power handling capacity where you are having, means silicon can have the more power handling capacity as compared to germanium. That's why I can write power handling capacity, power handling capacity, capability of silicon is higher than germanium only, is higher than germanium, I can say, than germanium. Power handling capability of the silicon is more only. That's why we are using practically. And also which is available very freely. Silicon is available. It is available on earth very freely only, we can say. Only from the sand we are going to get this silicon. Understand now. That's why we can write silicon is easily available on earth. Silicon is easily available on earth, I say. But all are on earth only now. But it is easily available. But the reason is what means it is extracted from this sand only. Understand my word now? That's why. Next one we can say leakage current, but now leakage current also whenever the bonds when the temperature is increasing in the semiconducting material, what is going to happen? Now, leakage current also possible in the electronic devices. Leakage current in nanoamperes are possible, where in silicon. Leakage current in germanium is in microamperes possible. So where we are going to get the more leakage current? In germanium made devices only. In the germanium made devices, when the temperature is increasing more and more, at the time leakage current is going to flow. When the leakage current is flowing in the circuits, means the required output is not possible to get only now. The required output you want to get means you should not allow any leakage current in the circuitry only now. But in the silicon we are finding nanoamperes, very less amount of the current only now. Understand? That's why we can write now leakage current is of order. Next point. Leakage current is of order nanoamperes, is of order nanoamperes. Where it is possible in nanoamperes? In nanoamperes in silicon. In silicon possible. In silicon is possible. While but now we can write it is in milliamperes, it is in microamperes. It is in microamperes in germanium. But if it is taken the germanium, you will find the microamperes, this leakage current. So where we are finding the less leakage current means only in the silicon itself now. That's why we are practically accepting only, you can say. But at room temperature, suppose you are maintaining the room temperature. At the room temperature, where you can find the conductivity more? Conductivity in the germanium is more or silicon is more? The conductivity of silicon is a less only possible. Less is possible now. Where? In silicon. But in germanium, you can find the more conductivity only now. At lower temperature, at room temperature, I can say. One more point. In this point of view, germanium is good only, you can say. Next point, at room temperature, when you are maintaining the room temperature to this germanium and silicon, conductivity of silicon is less than conductivity of silicon is less than germanium, I can say. So conductivity more in the germanium only, because energy band gap is a less where in germanium at room temperature. That is why the conductivity will be more possible there now. So these are all the points are required for germanium and silicon only here now. Understand my point? Next one, what I want to explain is based upon the mobility. I would like to explain certain things, certain important points I want to explain here now. Scattering. Next one is scattering. 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 There are two types of scatterings here now. There are two types of scatterings. One is said to be lattice scattering, second one is said to be impurity scattering. I will explain those two scattering because of this scattering phenomenon. What those formula will be here given, you will see them now. What I wish to say, there are two types of scattering. One is said to be lattice scattering. Lattice scattering, I can say. The second one is said to be impurity scattering, we can say. Impurity scattering. I will explain what is impurity scattering, what is lattice scattering. Like the two types of the scatterings are there now. The first one I want to explain, lattice scattering. Lattice scattering. What is the lattice scattering? First I'll write it now. Suppose as temperature is increasing in the semiconductor, you think it's so. As temperature is increasing more and more, mobility will be decreasing only now. Temperature is increasing means mobility is decreased in the material, then that scattering is said to be lattice scattering only now. Understand my word? I say as temperature increases, every point is very important. As temperature increases, mobility, where the temperature is increasing means why mobility is decreasing here now. Whereas the temperature is increasing, atoms are going to be vibrated only now. Vibration of the atoms are possible. Because of the vibration of the atoms, what is going to happen now? Mobility will be decreasing only now. That's why we can write as temperature increases, the vibration in element increases. The vibrations in atoms or elements, no problem. The vibrations of elements increases due to increase of temperature. Vibration of the elements are possible. Atoms are going to vibrate only now when they are vibrates, but because of the vibration of that, mobility will be decreased now, such that mobility decreases only here now. Such that mobility decreases. Mobility of charges. Mobility decreases only here now. That means in the lattice scattering, what phenomenon is possible? You try to increase the temperature to the materials. At the time, mobility will be decreasing only now. So a graphical curve is given for that. Mobility versus, I have taken now, mu versus log t I have taken here now. Ln of t I have taken. Ln of t. Ln of t. Ln of t. Whenever the temperature is increasing more and more, you think it's so. Mobility decreases, I said no. It comes the shape like this. That means when the temperature is increasing, log of t, natural log of t value increase. What now? This value also increases now. Mu also decreases now. That is the lattice scattering only now. In the lattice scattering, one formula is there now. At high temperature, this one now. At high temperature, when you are maintaining the high temperature, at high temperature only. When the temperature is maintained high, then only what happen now? Mobility will be decreasing. At high temperature, mu suffix, it's a lattice, mu L I have taken, lattice scattering. The mobility in the due to lattice scattering. Mu L is here directly proportional to t power minus 3 by 2 is possible. The relation is more important. You must remember this relation. The lattice scattering, mu L is directly proportional to t power minus 3 by 2. That means when the temperature is increasing more and more, and mu L will be, mobility will be decreasing only now. So this is the formula possible. Understand? And what about the impurity scattering? I will give. Impurity scattering. Impurity scattering. But in the impurity scattering, what we can say now, when the temperature is decreasing, the mobility will be decreased only now. Temperature decreases means mobility will be decreased. That is called as a impurity scattering only. I will give. Because of this is going to happen because of the structured imperfections only now. Because of the structured imperfections in the material, this is going to happen here now. This we can write one point out. Because of structured imperfections, because of the structured imperfections only, this is going to happen. Imperfections. In the before case, because of the vibrations of the elements, it is going to be decreased mobility when the temperature increases now. Because the structured imperfection, what happens now? Structured imperfection, the mobility decreases. The mobility decreases. The mobility decreases. The mobility decreases only. The mobility decreases by decreasing temperature. By decreasing temperature is called as impurity scattering only. That is called as impurity scattering. But in this case, how you can draw the diagram? Mobility versus mu versus, and I want to take here mu versus ln of t. Ln of t I have taken. But in this case, what now? When the temperature is decreased, mobility is decreased. At the time, the characteristic curve will come down like this. When the temperature decreases, mobility decreases because the structured impurity I said now. Understand now? But in this case, but how the relationship of between the mu and temperature is to be taken here now. Mobility because of impurity mu I want to take. Mu I is directly proportional to t power 3 by 2 I can write now. This formula very important. Temperature decreases means mobility decreasing now. Temperature increases means mobility will be increasing. The relation is possible between mobility and temperature only now. These are all the two types of the scatterings are possible. But we can write finally what is the total mobility in the what now? Material if it is taken. Total mobility, how we can find? 1 by mu equal to 1 by mu lattice plus 1 by mu I. Addition of these two can give the total mobility only now. 1 by mu equal to 1 by mu L plus 1 by mu I. From that you can find the mu only now. Understand now. Total mobility only now. Suppose the more scatterings are given in the problem. Suppose in a problem only 2 scatterings are given this now. Because of the any other scatterings it is given the what now mobility, so the more you think it so. What way we can find out the total mobility? I will give. Total mobility. Total mobility. Total mobility. Total mobility. Total mobility. If more scattering effects, if more scattering effects, then suppose more scattering effects are given, then how to find the total mobility? 1 by mu equal to, you must take 1 by mu 1 plus 1 by mu 2 plus, it's going on, 1 by mu 3, 1 by mu 3, 1 by mu 3, like that it is going on, plus etc. as it goes now. Like that you can compute the total mobility. By using this you can determine only now. Understand now? But the mu 1, mu 2, mu 3 are what not? Mu 1, mu 2, mu 3 are mobilities due to different scatterings only. Just now I explained. Understand now? So these are all the formulas also very important now. You will see the problems later on. Understand? But I said already, but how to find out the current density in the semiconducting material? How to find out the conductivity? These are all discussed here now. I will discuss now. But first of all, before doing the current density in the semiconductor, what are the types of the semiconductors are there? We can discuss. Then after we can find the required parameters here now. Understand my point now? But there are 2 types of semiconductors. One is said to be intrinsic semiconductor, second one is an extrinsic semiconductor. We can discuss those two only now. Understand? There are 2 types of semiconductors. There are 2 types of semiconductors. One is said to be intrinsic semiconductor. The second one is said to be extrinsic semiconductor. Like that you can divide. But an intrinsic semiconductor can also be called as a, one more name, this can also be called as a pure type of semiconductor. Pure type of semiconductor we can call. But again, extrinsic semiconductors are classified into 2 types. One is said to be N-type extrinsic semiconductor. The second one is said to be P-type extrinsic semiconductor. P-type extrinsic semiconductor. Like that we can divide. Initially, I would like to explain intrinsic semiconductor. Intrinsic semiconductor. How the energy band diagram of intrinsic semiconductor is to be drawn. I will draw here, you will understand. This is the energy band diagram of intrinsic semiconductor. But the gap will be maintained very less. This is the forbidden energy gap. Forbidden energy gap, FEG I have taken. This is the conduction band, you know, this is said to be valence band. In the energy band diagram, what is going to happen? Initially, it contains number of electrons. Where? In the valence band. There are number of electrons in the valence band. At room temperature, at 0 Kelvin. At 0 Kelvin, you can find electrons in the valence band. And conduction band is empty. The gap is very small. What is the forbidden energy gap? First, semiconductor I gave it already. I said that is a pure type of semiconductor. Slowly, I increase the temperature here now. When the temperature is increased, what is going to happen? Electrons are going to move from valence band to conduction band. Will go and occupy this. The electron will occupy here now. But once the electron is moving from valence band to conduction band, then finally it reaches to the conduction band. Once the electron leaves from valence band, thereby created one vacancy. Vacancy is nothing but the lack of electron. So one electron is moving from valence band to conduction band. What is going to happen? Thereby forming one hole, I can say. Thereby creating one hole. Here creating one hole. Electron is moved from valence band to conduction band. Then electron is in the conduction band, hole is created. This is said to be hole. What is holes are? Hole is nothing but the lack of electron. When the electron is moving from one point to the other point, in the first point it is creating one vacancy. Suppose like that, what now? Number of electrons are moved from valence band to conduction band. You like this, you think it's so. Suppose number of electrons are moved here now. If number of electrons are moved means what is going to happen here? Now please watch what happens now. Suppose here the 4 electrons are reaching to this point. First electron, second electron, third electron, and 4 electrons reach to the conduction band. How many number of the holes are created? How many vacancies are created? 4 vacancies are created here now. This is one vacancy and one more vacancy, third vacancy and 4 vacancy. How many number of electrons are moving from valence band to conduction band? That many number of holes will be created in the valence band only. There's in the intrinsic semiconductor, we can say number of electrons number of electrons in conduction band is equal to number of holes in the valence band. Number of holes in valence band. Number of electrons in the conduction band is denoted by symbol N. Number of holes in the valence band is to be taken with a P. Holes are denoted by symbol P. Concentration of electrons N. N and P are equal in intrinsic semiconductor. So you followed here now. But in the practically, are you using any intrinsic semiconductor in designing the electronic devices? We are not using. Why we are not using the pure type of semiconductors means the conductivity in intrinsic semiconductor will not be more. That's why we are using the extrinsic only now. Extrinsic why we are using now? When some impurity is doped there only now. Because of the increase of the because of the addition of the impurity, conductivity of the material will be increasing more and more. That is why they are going to select extrinsic semiconductor now. Even you want to design the PN junction diode P-type and N-type material we are taking now. Even you want to design the transistor, that means NP and PNP, N-type and P-type only now. Even you want to design the JFET, even you want to design the MOSFET, it is required extrinsic semiconductor only now. But extrinsic semiconductor I can get only from the what now, intrinsic semiconductor only now. For the intrinsic semiconductor, some doping is to be made. Without doping we can't get. Without intrinsic semiconductor I can't get extrinsic semiconductor. Anyhow, the information what you have to remember here is a pure type of semiconductor is called as intrinsic semiconductor. It contains number of electrons and number of holes equal. What number of electrons means now? When the temperature is applied, number of electrons move from valence band to conduction band. When the number of electrons are reaching to the conduction band, that many number of the holes are creating in the valence band. Those two are equal only, we can find only now. Understand my point now? So the information I will give in the today class. The next class one I can explain the mass section law and also what no different parameters from the intrinsic semiconductor. I hope so far you followed and enjoyed the class. Okay, thank you all.